Human Immunity by Catherine White. So when we look at the first lines of defence, the largest is the skin. It is the biggest organ of the human body and replaces itself every 28 days. Comprised of 3 layers, the epidermis, the dermis and the subcutaneous layer. And as long as the skin remains intact, it acts as an effective barrier to hinder penetration of microbial organisms and to restrict the penetration of chemical irritants, impede penetration of toxins. It absorbs and blocks solar and ionised radiation, and it also prevents the loss of water within the body. However, there are some occasions when the skin does not protect us. Insects such as mosquitoes can penetrate the skin and cause infections and diseases such as malaria, Lyme disease and yellow fever. If the skin is broken, bacteria can enter the body and cause infections like cellulitis, impetigo and tuberculosis. Another first line of defence are the mucous membranes, which line the surfaces of the eyes, ears, nose, sinuses, mouth, throat and the gastrointestinal tract, respiratory tract, urogenital tract and the vaginal tract. They are the primary interface between external and internal environment of the body, and they secrete mucus to trap organisms, pathogens and allergens to prevent them entering into deeper tissues. When this fails, infections and diseases occur such as chickenpox, the common cold, influenza and whooping cough. The gastrointestinal system also contains a series of barriers to help prevent infection, for example, stomach acid, bile, pancreatic enzymes and intestinal secretions. When the barriers do not work, illnesses can develop like gastroenteritis, E. coli and norovirus. The second line of defence is the immune response. This is a group of tissues, organs and cells which work together, known as the immune system. Leukocytes are white blood cells utilised in defence, and they look for and destroy foreign substances and disease-causing organisms. There are 3 main types of leukocytes. Macrophages, important part of the immune system, formed from white blood cells called monocytes, and when an infection or accumulation of damaged cells occur, they recognise as damage and destroy them, and they are very versatile to form different structures to fight infections more productively. Neutrophils are the most generous type of white blood cell and the major defence against pus-forming bacteria. They are usually the first to arrive at an infection site and have the ability to move through blood cells. Cytokines are small proteins produced by a number of various cells to enhance the immune response by communicating and mediating inflammation and immunity. Their existence cause further cytokines to be released. The tissues and organs involved are the lymphatic system, lymph nodes and lymph fluid. When pathogens enter the body, neutrophils gather around the entry site to submerge the pathogen and help to eradicate it. They will then dispose of the waste. This is called phagocytosis, and this will send signals to other cells to call for help, as you can see from this diagram here. The dendritic cells may find a pathogen and present it to the T helper cells, which converge in lymph nodes throughout the body. If the T cells recognise the pathogen, it will begin duplicating to increase the numbers so that there is enough to activate the immune cells needed for the attack. The increase in blood circulation, the various cells of the immune system and proteins which fuel the immune response congregate around the infected area, resulting in inflammation. The heat increase at the site of infection can have an antibiotic effect, aiding the body to rid the infection. The common signs of infection are as follows. The tissue takes on a red colour because of the increase of blood cells to the area. The tissue becomes swollen because histamine makes the capillaries more accessible than normal. The affected area is painful and sore, as shown here, and the individual can get a fever in response to pyrogens which stimulate the fever. But once the infection has passed, the area will return to normal. So pathogens are the third line of defence are when pathogens are an infection agent. The main ones are bacteria and viruses, but there are also fungi and protozoans which can make an individual ill. Bacteria are a single-celled organism such as Streptococcus and cellulitis. They are too small to be seen by the naked eye, but viruses are even smaller and are not technically living organisms. Antigens are parts of the pathogen which will inform your body that it is being attacked, and they cause the immune response within the body. They can be any type of molecule, for example, proteins or nucleic acid, which the pathogen needs to enable it to infect the body, and it is constantly battling against the body's ability to recognise the antigen and stop the infection. The body does have the ability to become immune to some of these pathogens, and this can be done by 2 ways. Acquired immunity, not present at birth, and the body learns it when it is exposed to the natural environment. The immune system encounters antigens and decides on the best way to invade it. It will then begin to acquire a memory for that antigen, and the immune system will then tailor its invasion based on its previous encounter with it. The immune system is very clever for its ability to learn, adapt, and remember. Artificially acquired immunity can be given via two mechanisms, but both of which involve human intervention. It can be given actively when the body is deliberately exposed to the foreign antigen by way of vaccination, or it can be done passively by introducing preformed antibodies to generate a protective immune activity. The third line of defence are the leukocytes, which are white blood cells and are the fundamental element of the immune system. There are 5 types which are produced in the bone marrow and are involved in defending the body against infections and foreign bodies. Lymphocytes are small and round. It's a major part of the humoral immune system, which relates to antibody production. T lymphocytes are necessary in cell-mediated immunity, and B lymphocytes make antibodies needed for disease resistance. Monocytes, which are the largest but less common, agranulocytes, which mean they have less granules in their cytoplasm. They turn into macrophages when they exit the bloodstream, and their size gives them the ability to digest large particles, and they do the job of phagocytosis of any dead cells. Basophils are the rarest white blood cells. It's known that they have large granules, but their function is not well known. They secrete anticoagulants and antibodies to act against hypersensitivity reactions in the bloodstream. Eosinophils are rare white blood cells, and they have large granules which release toxins to kill pathogens. They are critical to allergies and worm infestations. High counts of them are associated with allergic reactions. Neutrophils are the most common white blood cells, medium with irregular nuclei and many granules which conduct a number of various functions. They are the first to reach an infected area and attach to the walls of blood vessels to try and stop germs entering the bloodstream through a cut. So, looking further at the third line of defence, T cells mature in the thymus gland, which gives them their name, and there are 3 types: cytotoxic, suppressor, and helper, all of which have a role in the annihilation of problem cells in the body. Certain substances which are released into the bloodstream help the T cells to function. As they cannot detect problem cells alone, they require the help of APC to present part of the foreign substance to the T cells. They also signal for growth and activation of the B cells. The APC have molecules on their surface which allow them to communicate with helper cells. The T cells are released into the bloodstream to give them the responsibility of the destruction of foreign substances. B cells maturation occurs in the bone marrow, and when they're not actively engaged in an infection, they remain in the lymph nodes. They have 2 major functions. The first is the production of antibodies, and the second is to present antigens to the T cells for activation. Once activated, they produce large amounts of antibodies. B cells form the memory after they have been stimulated and remain in the lymph nodes should the specific antigen be encountered again. Immunoglobulins have a number of different functions in the body, and they are normally made up of 4 chains, 2 of which are heavier and 2 of which are lighter. Immunoglobulin G is a major activator of complement pathways, and they help in the direct attack of foreign substances. It's the only one that can be passed from mother to baby. Immunoglobulin A, important in the cellular defence of the soft mucosal surfaces of the body, such as the mouth. Immunoglobulin M has a different structure from the others. It has 5 Igs joined at the base, and it is the first Ig synthesised in an antibody response. Immunoglobulin T responds to parasitic and allergic reactions when their normal low levels increase significantly. And finally, immunoglobulin D is quite uncommon and its function remains unknown. So the unique nature of antigens allows the immune system to distinguish between self and non-self antigens, allowing only the non-self to be annihilated. To do this, 2 important factors are needed to be contemplated. The major histocompatibility complexes 1 and 2, MHC1 and MHC2, and the human leukocyte antigen gene complex. When a non-self antigen is identified, the innate and adaptive immune systems will follow. The level of response can vary significantly. The number of similarities between self and non-self antigens determine the level of response. Antigens which are vastly different from the self will initiate the strongest response. MHC1 are glycoproteins on the surface of all nucleated cells, and they act as an early warning system to the immune system. If the cell contains foreign proteins, the MHC1 will disintegrate it into fragments on the cell surface and present it to be recognised by the immune system, such as the T cells. They are also responsible for the rejection of transplanted organs. MHC2 have a similar function, but they are only present in certain cells of the immune system as opposed to nucleated cells. They present antigens from extracellular pathogens such as bacteria. The pathogens are endocytosed by B cells and phagocytes, where they are digested using lysosomes. Then the antigen fragments are presented on the surface and picked up by the T cells. The human immune system is extremely complicated in its response to antigens and pathogens. There are different levels of sensitivity to all antigens. Hypersensitivity is an abnormal immune reaction caused by immune response, which is exposed repeatedly to the same antigen. Diseases which are hypersensitive tend to manifest into chronic problems. Autoimmunity is the response of the adaptive immune system to self-antigens which develop when the system of self-tolerance fails. The immune system can produce different types of cells, different cell types, and each one can respond to different and specific foreign antigens, and the immune system is constantly cloning and generating these cells, continually culling the self-reacting cells from the final pool. If it fails or the process is incomplete, the B and T cells will be produced to aid the destruction of rogue cells. What's quite miraculous is that none of these cell types have any reaction or impact to self-antigens. The basis of autoimmune disease is when the rogue cells or the products react against self-antigens. So, the rejection of transplanted organ. What is a transplant? It is a transplant. A transplant is when cells, tissues, or organs are transferred from one person to another to replace damaged ones. The immune system is a formidable barrier in the process due to its capability to fight foreign agents. The immune system of the person receiving the transplant may reject it because the immune system recognises it as foreign. Why? Tissues and organs which are not matched closely enough mean the immune system will detect that the cells are different and cause reaction. Monoclonal antibodies can be used during and after surgery to rid the body of specific T cells which cause rejection. Otherwise, the body will almost certainly destroy the foreign tissue. There are 3 types of rejection. Hyperacute, which occurs within minutes of the transplant, usually because antigens have been completely mismatched. Acute occurs anytime from 1 week to 3 months after the transplant, and chronic rejection occurs over many years because the organ is damaged by the body's chronic immune response, constant immune response. So, autoimmune disease. There are more than 80 autoimmune disease types. They can be very difficult to diagnose, as some are similar to others. They are wide-ranging and can affect any part of the body. They occur when the immune system mistakenly attacks healthy cells. So we're going to look at 2. The first one is fibromyalgia syndrome. It is a condition which causes pain throughout the body, and symptoms include muscle stiffness, issues with mental processes, difficulty sleeping, headaches, tender joints, and exhaustion. It is 7 times more likely to affect women than men. Its cause is currently unknown, but it is believed that abnormal levels of chemicals in the brain change the way the central nervous system processes pain messages. Some people are more likely to develop the disease because it can be inherited through genes. In some instances, fibromyalgia can be triggered through emotional or physical stress such as an operation, giving birth, or the death of a loved one. But we do know that it is not caused by inflammation or wear and tear of the muscles and joints, and there is no tissue damage. Exceedingly difficult to diagnose because there is no specific test for the condition, and many of the symptoms can be similar to other conditions such as multiple sclerosis. There are a number of trigger points which, if tender when examined, could be a sign of it, especially if there are no other muscle diseases present. There are currently no cures, but there are a number of treatments available such as medicine, exercise programs, and relaxation techniques. So the second one is Crohn's disease, which is an inflammatory disease which affects the bowels and gastrointestinal tract. And it can affect any part of the tract from the mouth to the anus, but is more common in the colon and small bowel. It can be developed at any age, but more common for people to be diagnosed between the ages of 20 to 30, and more likely to develop if the individual has a close relative with the disease. It is more common in Caucasian people, but can affect people of all ethnic backgrounds. The cause of it is currently unknown, but it's believed that factors such as genes, smoking, stomach bugs, and immunity problems are related to people developing it. The main symptoms include, but not limited to, diarrhoea, bloody stools, tiredness, weight loss, and constipation. Severe cases can cause anal fissures and fistulas. There is currently no cure for Crohn's disease, but a number of treatments can help alleviate the symptoms, such as medicines, surgery, and lifestyle changes, such as changing the diet, stop smoking, and exercising more. Acquired immunity occurs when individuals are exposed to the pathogen or its antigens. This can be in two ways, either naturally or artificially. Natural acquired immunity develops when an individual is naturally exposed to a pathogen which creates a specific disease. The immune system responds as soon as the infectious pathogen enters the bodies, and the T cells attach themselves to the pathogen and will take it to B cells, which generate the antibody needed to fight and eradicate it. B cells then create the memory to the antibody, which provides long-term immunity to that particular pathogen, so that if it infects the body again, the cells will become active again. Measles and chickenpox are examples of this. Artificial acquired immunity develops when an individual is purposely and artificially exposed to the virus or bacteria responsible for developing the disease in order to develop a protective immune response. The method in which this is done is by giving the individual an injection or transfusion of the antibodies, which are specially prepared. This can only be executed through human intervention, and the immunity only normally lasts a couple of weeks. Passive acquired immunity is formed after an individual receives antibodies produced by another individual. It can be passed between mother to child through the bloodstream in the womb and can also be transferred through breastfeeding. Immunity diminishes between 4 and 6 months. So some of the artificial pathogens that can be used to boost immunity are dead pathogens, harmless fragments of a pathogen, live pathogens which are treated to make them safe, and toxins produced by pathogens. A weakened or harmless version of these are injected into the body, but there is no danger of developing the specific illness, although some mild symptoms can be encountered. When the immune system encounters these pathogens, the white blood cells are stimulated to produce antibodies to fight the pathogen. The primary response is when the pathogen is experienced for the first time, and the B cells take some time to identify the antigen and plasma cells to manufacture the correct antibody. Unfortunately, this can allow time for the infection to take hold and symptoms begin to develop. Memory cells are created at this point. The secondary response is when the pathogen is experienced again. The memory cells, which have already been encountered, recognise the pathogen and quickly produce larger quantities of antibodies so they can fight off the infection before symptoms begin to appear. This can happen many years after the pathogen was experienced for the first time. The immunological memory is where the antigen-specific lymphocytes have been made in the primary response, transform into effector cells, and can immediately respond upon re-exposure to the antigen. The memories will differentiate into plasma cells and increase the output of the antibodies. So looking at measles in the UK since 1940, we can see by this graph that prior to the vaccination being introduced in 1968, the number of confirmed cases was astronomical. Looking at in the 1940s alone, there was nearly 3.5 million, and the amount of deaths, while still a lot higher, is a small percentage compared to the amount of cases. Since the vaccination was introduced, we can see that the number of both confirmed cases and deaths decreases rapidly. In 1940s, the deaths were approximately 0.17% of the confirmed cases, whereas now it is more like 0.02%, thus proving that the vaccine is extremely effective at providing immunity. Not only has it decreased the number of people contracting the disease, it has also decreased the proportion of people dying from it. So finally, we're going to look at herd immunity and vaccination programmes. So basically what these want to do is, by vaccinating a large proportion of the population, it is more challenging for contagions to spread, so it limits the number of individuals could become infected, therefore increasing the capability of stopping the spread. Herd immunity cannot protect from all diseases which can be vaccinated against. For instance, tuberculosis is spread from bacteria, not from human to human, as it is infectious but not contagious. The number of people that need to be vaccinated against to provide herd immunity varies with each disease because each contagion has different characteristics. There are, however, a number of issues with trying to provide herd immunity. Individuals can become infected before the vaccination takes hold. There's many different variants of the pathogen, and some people will fail to exert an immune response, and some people just simply don't want vaccinations. The pathogen could also be undetected by the immune system, and pathogens can mutate very rapidly. Many years ago, when people travelled less and communities were smaller, it was easier to contain transmissions, but now it's easier for people to transmit diseases. Vaccination programmes help to maintain herd immunity in diseases such as measles, mumps and rubella. The majority of young children have these vaccinations in their early years. Currently, the world is going through a rigorous vaccine programme to help tackle COVID-19, and the idea is that by starting with the most vulnerable people and working through different categories, we as a whole will be able to gain herd immunity. But some parents worry about the safety of vaccinations, and some concerns have been proven to be correct, and some have been proven to be unsubstantiated.